In this lesson, I want to talk about the Catalan numbers. First, let's start with a related problem about counting paths in the plane. Let's define a lattice path to be a path with steps going 1 unit up and 1 unit to the right. So if we start at the origin and pick a point where we're going to end, say from 0, 0 to A, B, then it's easy to count the number of lattice paths there. There are A plus B, choose A, which is the same as A plus B, choose B, lattice paths. So example, if AB is 2, 2, then we can go up twice and over twice. Up once, over once, up once, over once. Up once, over twice, and then up. Over once, up twice, and then over again. Over, up, over, up. Over, up, up. And I guess that's it. So 2 plus 2, choose 2 is 4, choose 2, which is 6, and I have 6 paths there, so that makes sense. And the reason why this is true is because to get from 0 to 0 to AB, we have to go over A times and up B times. So that's a total of A plus B steps. And then if we choose A of those steps to go to the right, well, if we're going to AB, we have to choose A of those steps to go to the right. Equivalently, B steps up. And we can do that in A plus B, choose A ways. All right, but what I want to really look at is a harder problem. I want to look at the question of how many lattice paths from the origin to NN never cross below the line y equals x. So for n equals 3, let me put a couple of grids up here. So we don't ever want to cross below y equals x. We can go 3 steps up, 3 steps over, 2 up, over, up, 2 steps over, up, over, 2 steps up, 2 steps over, 2 steps up, 2 steps over, up, over, or up, over, up, over, up, over. So there's exactly 5 where n equals 3. And I claim that there are in general 1 over n plus 1, 2n choose n, such paths. To prove this, let's first note that 1 over n plus 1, 2n choose n is 2n choose n minus n over n plus 1, 2n choose n. So 1 over n plus 1 of anything is anything minus n over n plus 1 of anything. And I want to express that last term there a little differently. Also, I want you to note that n over n plus 1, 2n choose n, is n times 2n factorial over n plus 1, n factorial, n factorial. This is n plus 1 factorial. And then if we cancel n with the n and n factorial, then we've got an n minus 1 factorial down there. So we could write this as 2n choose n minus 1, or if we like, 2n choose n plus 1. Now also, I want to note that the number of lattice paths from 0, 0 to n, n not passing below y equals x equals the total number of lattice paths 0, 0 to n, n minus the number that pass below y equals x. Now the total number of lattice paths from 0, 0 to n, n is 2n choose n. And we're claiming that the lattice paths from 0, 0 to n, n that don't pass below y equals x is precisely this number here, 1 over n plus 1, 2n choose n. So to prove that, it would suffice to prove that what we're subtracting here is precisely that term. In other words, 2n choose n plus 1, equivalently 2n choose n minus 1. Because if those terms are the same, and we can see that these terms are the same, then the left-hand sides must be the same. So we claim that the number of lattice paths passing below y equals x is 2n choose n plus 1. And that'll be sufficient to prove the claim. All right, to see this, let's observe that any lattice path crossing below y equals x must touch y equals x minus 1, because these are all unit steps. So if you pass that line y equals x, then you go one step further and you're touching the line y equals x minus 1. So there's y equals x. There's y equals x minus 1. And if we ever, touching this line is okay, but if we go one step further, then there we go, and we've hit the other line, y equals x minus 1. So equivalently, we want to claim that the number of lattice paths from 0, 0 to nn that touch y equals x minus 1 is 2n choose n plus 1. So I could change this to say the number that touch y equals x minus 1. And I could change this to we claim that the number of lattice paths 0, 0 to nn touching y equals x minus 1 is this number. Now this is also the number of lattice paths of 2n steps that contain n plus 1 steps upward and n minus 1 step to the right. So I could say from 1, negative 1 to nn. Because if we go from 1, negative 1 to nn, then we're going to the right n minus 1 steps, and we're going up n plus 1 steps. Alright, now what does this have to do? Let me put another picture here. So let's say here's the origin. Here's y equals x. Now if we go from 1, negative 1 to nn, What does that have to do with paths that start from 0, 0 and go to NN and pass below, or sorry, touch the line y equals x minus 1? Well, if a path starts here and touches the line y equals x minus 1, then we can reflect this initial section from the origin to the first place it touches y equals x minus 1. To get a path from 1, negative 1 to NN. Because if we're reflecting in the path y equals x minus 1, 0, 0 reflects to 1, negative 1. Conversely, if we have any path that starts at 1, negative 1 and goes to NN, 1, negative 1 is below this line, y equals x minus 1, and n is above it. So that path has to touch this line y equals x minus 1 at least once. So we can take the first place that it touches and then reflect that initial segment across the line y equals x minus 1 and get a lattice path from 0, 0 to NN. Furthermore, that path that we're going to get certainly touches the line x minus 1, because as we said, we're starting below the line x minus 1, ending above it, so we certainly touch that line. And then we reflect the initial segment up until that touching point. We still keep that touching point. And so we get a path from 0, 0 to NN that touches the line y equals x minus 1. So since there is a bijection between lattice paths from 0, 0 to NN that touch y equals x minus 1, and lattice paths from 1, negative 1 to NN, we have that the number of lattice paths staying at or above y equals x is 2n, choose n, all the lattice paths, minus the bad ones. And we said before that this is 1 over n plus 1, 2n, choose n. Let's plug in a couple of values of n here. When n is 1, we've got 1 over 2, 2 choose 1, so that's just 1. When n is 2, we've got 1/3 of 4 choose 2. 1/3 of 6 is 2. When n is 3, we've got 1/4 of 6 choose 3. So that's 5. When n is 4, we've got 1/5 of 8 choose 4. So 1/5 of 8 times 7 times 6 times 5 over 4 times 3 times 2. 5's cancel, 3 times 2 cancels with 6. 4 cancels with 8 to make 2, so we've got 2 times 7, 14. I'll just write the next number here. When n equals 5, we get 42. Now the Catalan numbers count not only lattice paths from 0, 0 to n that don't pass below y equals x, they count a bunch of other things too that are in bijection with these lattice paths. So a related question is, how many sequences of n 1s and n minus 1s have all non-negative partial sums? So for n equals 3, we have 1, 1, 1, minus 1, minus 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1, 1, minus 1, 1, minus 1, minus 1. So the trick is to always write down more ones so far than you've written down negative ones. 1, negative 1, 1, 1, negative 1, negative 1. 1, negative 1, 1, negative 1, 1, negative 1. So I think that's it. There's 5 of them. Now the third number in our sequence here is 5. So it's possible that these are in bijection with the lattice paths. The answer is 1 over n plus 1, 2n choose n. And the bijection is pretty easy. We can turn every 1 into an up step, and every minus 1 into a step to the right. And always having non-negative partial sums is the same as always having more 1s than negative 1s so far, which is the same as having more up steps than right steps so far, and therefore not crossing the line y equals x. So up, up, over, over, up, over, up, up, over, up, over, over, up, over, up, up, over, over, and up, over, up, over, up, over. So we call 1 over n plus 1 2n, choose n, the nth Catalan number. After a French mathematician named Catalan that studied them. Let's look at some more questions whose answers are Catalan numbers. One is, how many properly nested sequences of n pairs of parentheses are there? So if we write down for n equals 3, the proper nested sequences of parentheses, we could have open, 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 close, 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 or open, open, close, close, open, close, open, close, open, open, close, close, open, open, close, open, close, close, or open, close, open, close, open, close. So those are all the ways of writing 3 pairs of parentheses that make sense. And these are in bijection with lattice paths, sort of for the same reason that the ones and negative ones are in bijection with lattice paths. Because properly nested sequences means that you don't close more parentheses than you've opened so far. So to do this with the lattice path, we could say open, open, close, close, open, close. So every up step is an open, and every step to the right is a close. Another question is, in how many ways can we create a non-crossing perfect matching of 2n points on a horizontal line with all arcs above that line? So for example, let's do n equals 3 again. So we could do this perfect matching, or that one, or that one, or that one, and there should be one more. Here we go, that one. For n equals 3, there's 5. And we can see that these objects are counted by Catalan numbers, because if we look at the left endpoint and the right endpoint of every arc and put a parenthesis underneath them, left parenthesis to start, right parenthesis to end, then we're going to get the sequences of parentheses that we know are counted by Catalan numbers. These are really just the diagrams that show